We're going to start off in chapter 14, and we're going to look at a couple of the different examples. I'm going to pick some out. If you have questions about any specific ones, then we'll take those one at a time. So the first one is, we'll just start with number 1. Okay, this one is about sample space and possibilities. So I'll just read it to you. If you have your book out, please get it out. It's on page 338. We're in chapter 14, sample spaces. For each of the following, list the sample space and tell whether you think the events are equally likely. Okay, so toss 2 coins. Okay, so 2 coins is what I'm really looking at. Well, let's write the sample space out. When you write out sample spaces of probabilities, okay, tree diagrams are the easiest way to go. With only 2 tosses, this one's probably really easy. But if I got into like 5 tosses, then it becomes, okay, I've got 5 outcomes that I have to keep up with. Did I get them all? Or did I repeat some? I'd rather not leave that up to just getting lucky, or if I'm in the stress of a test, I don't want to have to analytically try to reason out without any technique. And so this is how I'll do this one. The first part, I could get heads or I could get tails. That would be my first. Each row, every time I split it, is another outcome. Right? So I could get heads or tails the first time. So that means I have 2 outcomes. If I flip a coin again, that means I have 2 more outcomes. So how many outcomes should be in my sample space? 2 times 2, which would be 4. Okay. For example, if I keep this going, what if I flipped a coin 5 times? How many outcomes should be in my sample space? 2 to what power? 2 to the 5th power. That would be 32. Okay, 2 times 2 times 2 times 2 times 2 would be exactly 32. So when I'm writing out the sample space, that's another way for you to say, do I have them all? Right? So it's really just multiplication of every outcome. For example, if we do something a little bit more trivial, what if you had a pizza shop that had 2 types of crust, right? So just side example, 2 types of crust. Let's say they had 3 types of cheese and they had 8 different veggies. Okay? Same sauce. Let's suppose, and let's keep it simple. So this would be the bread, this would be the cheese, and let's just say this is toppings. Okay? If I get to choose one of each one of these things, how many different varieties of pizzas could I make? 48. 2 times 3 times 8. Now it gets more complicated if I get to pick more than one. But if I just get to pick one of each one of these things, then I would have 48 different outcomes in my sample space. Okay? Just like if you have let's be realistic. You have 20 pairs of shoes, okay? 10 pairs of jeans, and you have like your favorite 5 shirts. How many different let's assume they all go together. How many could you put together? I'm just saying you'd multiply them all together, right?
Yeah.
Lots. Way too many is really what the answer is. Because it's 2 times 2 times 2 times 2. It's the same thing every time. If the outcomes are the same number each time, then I can take it to a power. But really what I'm doing is 2 times 2 times 2 times 2 5 times. If the outcomes are different for every event, like that time it was bread versus cheese versus toppings. So each thing had a different number of outcomes. Anyway, let's keep going. Right? And so we have heads, tails again, heads, tails again. And so what we end up with, so my sample space would be what? The tree diagram does not constitute sample space. Tell me what I could. I could have heads and heads. I could have heads, tails. So that would cover those 2 parts. Tails, heads, and then tails, tails. Those 2 parts. So the question says, toss 2 coins, record the order of heads and tails. We just did that. There are 4 different ways it could occur, and this is the order. Any questions about that part? Okay, so let's see, this is part B, right? So 1, part B. says you're going to have a family that has 3 children. Be careful. Record the number of boys that could occur. Right? So now I'm not just talking about heads and tails. So we'll do it. Let's make our tree diagram, and then let's convert it to the right way of answering the question. And so if we start out with 3 kids, we could have boy, girl, boy, girl. Go all the way down 3 times. Boy, girl, boy, girl, boy, girl, boy, girl. So writing this one out takes a little bit more effort because I've got 3 steps to go through. And so if I come over here on the side, let's write out the sample space. So I could have boy, boy, boy. So that would end up being 3 boys. Okay. I could have boy, boy, girl. That would be 2 boys. I could have boy, girl, boy. That would also be 2 boys. Get a boy, girl, girl. That would be 1 boy. So I really took care of like all 4 of the outcomes that we have. 1, 2, 3, 4. I kind of worked my way from the top down to the bottom of each of those pieces. Does that make sense so far? Okay, let's go on the other side. I could have girl, boy, boy. That would still be 2 boys. Then I could have girl, boy, girl. That would also be just one boy. We could have girl. Let's see, girl, boy. That would be 1, and then girl, 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 which would be 0. So that would give me 1, 2, 3, all 4 of those. So I have 8 outcomes. Let's double check. 3 children. I'm going to have 3 children. What are the possibilities? How many should be my sample space? It's 2 outcomes times 2 outcomes times 2 outcomes, or 2 cubed, which is 8. And I have 8 different things. So if I were to write out the answer to this one, what's the possible outcomes here? Remember, I'm counting boys. So what is my actual, for the way that the question was worded, what's my actual sample space? 0, 1, 2, 3. The question wasn't list the order of children or how your children, what the gender of your children. Do you think the question was, a family has 3 children, record the number of boys? Well, it could be 0, 1, 2, 3. Now, let's go back a minute. One thing we didn't talk about in the question 4. Are these outcomes all equally likely to show up? Okay, in the point example, yes, they are. Look at this one. Remember, what you're looking to count, the outcomes it changes. So, is 0, 1, 2, 3, are they all equally likely to show up?
Yes.
Well, back up for a minute. What are you looking at to try to decide? Or are you just guessing? Look up on the screen. I wrote them down how often they occurred. Are they all showing up the same number of times? In fact, no. Look at this. 3 and 0 occurred only 1 time, but 2 and 1 both occurred 3 times. So, absolutely not equally likely. Does that make sense? All right. And we'll skip. I'm going to skip D. It's the same thing over. I want to move on to something different. Okay? But do you get the idea? Writing down sample space is one thing. Determining if they're equally likely, well, I could figure out the probabilities. In this case, it's all 0.5, right? But some of those, like 3 only occurs 1 time. 0 occurs only 1 time, but 1 and 2 occur more often. They're more, so I'd have to add those probabilities together. So it'd be 0.125 plus 0.125 plus 0.125. Having no boys or having 3 boys, you have a 0.125 chance or 1/8 chance of happening. but the others are 3/8 chance of happening. All right, let's go on to the next one. Number 19. Okay, this was about car repairs. The consumer organization estimates that over a 1-year period, 17% of cars will need to be repaired once, 7% of the cars will need to be repaired twice, and let's see, what else? And 4% will require 3 or more repairs. What's the probability a car will need the following number of repairs? And you're looking at it based on the probabilities that they gave you in the previous paragraph. All right, so no repairs. All right, so this is going to be, this is number 19. So what's the probability you have 0, or that x would be equal to 0 number of repairs? How would I do that? That would be exactly right. If you can hear that, add up all the probabilities. Okay? Because what I didn't give you was the probability of not having a repair at all. That's the one thing I don't have. And remember, this is almost like the same as at least 1. Although they didn't write it in that form. They specifically said, what about 0? And so it would look something like this. And so you'd have, let's see, 0.17 plus 0.07 plus 0.04. And that would give me 0.28. So we'd say 1 minus 0.28, 0.72. Because what really we're looking at here, this is for some repair. I don't care how many. As long as it got repaired, then that's that probability. So if I subtract that, remember this covers everything. You either had no repairs, 1 repair, 2 repairs, or 3 or more. That covers all types, all numbers of repairs. Okay, part B. What about no more than 1 repair? Let me kind of bring this back for a minute, because there's something we can write down that would make this a lot easier. Probability distribution. We talked about this when we were doing chapter 14. One thing we said about probability distributions was that in order for them to be valid, they all had to have a probability between 0 and 1 inclusive, and that all of the probabilities added together must add to, yes, 1. So we're going to write this out. My outcomes are x. The probabilities are p of x. Well, I could have 0 repairs, 1 repair, 2 repairs, and then 3 or more repairs. So we'll write it out like that. Yes. So what we're going to do, we talked about probability of 0. That's already done. That's 0.72. What's the probability of getting just 1 repair? And what about 2 repairs? And then 0.04. So now, if it asks me for anything, I don't care, 1 repair, 2 repairs, what about 3 or more? What about between 1 and 3? I have every possible outcome written for me, and I can add as I see fit, or subtract, whatever the question is. This question says, what's the probability of getting at least, what was it? No more than 1. So when it says no more than 1, what am I talking about? What?
1 is 0 and 1.
0 and 1. So 0.72 plus 0.17 would give me what? So 0.89. So there's an 89% chance that you would have no more than 1 repair. Piece of cake. What allows me just to add these together without having any problems with it? What do we know about these? Because they're not independence. Independence has to do with multiplying. They're disjointed. You can't have 1 repair and 2 repairs. If you had 2, you had 2. So because each of these outcomes are disjoint, I can write this thing right here. Okay. If I had jointed outcomes, I would have to write a Venn diagram. Okay. If I don't have a Venn diagram, I can write this thing. This is a lot like tree diagrams. Tree diagrams have disjointed outcomes, so I can write those out. All right, part C. What about some repairs? How do you know? Because that's what we did to start with, but we subtracted it, right? Look at what I wrote down. Some repairs. Okay? It's as long as you had 1 or 2 or 3 or more. So you find those outcomes, you add them all together. Any questions about this one? The tree diagram, the little probability distribution table really makes it easy to do this kind of problem. It's not always able to do it. I got to know all the outcomes, and I got to know their probabilities. Something to note, if I gave you 3 of them, like, for example, I didn't give you 0 here, did I? But that's one of the first things we found. Once I found that allowed me to write the whole table out, because I knew they added to 1 anyway, so I could have figured any one missing one. Let's look at another one. Let's see, 21. 21 says, consider the auto repair. So this is just a kind of an extension of the last one. And what if you own 2 cars? What's the probability that... So let's back up for a minute. Let's write out... So this is number 21. Let's go back to my table and write those probabilities back out. So actually, let me do it the easier way. I think I can copy and paste this. Copy. Paste. Sweet. Okay, so we've got this from last time. They want to know the first part. So what is the probability that neither car will need repair? So in this case, again, we're looking at x equals 0, but this is for both. So if we wrote that out, what's the probability of, let's say, x equals 0 and the probability that y equals 0? Ooh, what are we doing here? Y. Hold on, let me write that down. You said 0.72 times 0.72. Why is that? It's because it's what? You're right, it's and. But remember, we can't just always multiply stuff together. What do I have to think about? What has to be true in order for that to happen? Try again. Independent. Listen carefully. This is where independence and disjointedness start to mix for some of you. And you're not sure about which is which. Multiplication has to do with independence. Adding, or most of the time it's just adding, will have to do with disjointedness. So if I go to multiply, if I have 2 things happening, in order for you to contemplate independence, you've got to have at least 2 events. You can't have independence problems when there's only one event to occur, because independence says that the first outcome of the first event influenced the outcome, the probability of the second event. So if there's only one event or one situation happening, then you're probably not going to be dealing with independence. Okay? Next part says, what about both will need repair? What was the probability that you need a repair? Some repair.
Some repair is 42.
It's the probability of some, right? And so that would be 0.28 times 0.28. Is that right? Let's check. Exactly right. Okay, so if I need some, that means we found that one in the last one. Some would be 1, 2, or 3. So I added those together for the first one, multiplied it times the second because they are independent. The chance of one car breaking down has nothing to do with the other car breaking down. Okay? In the rare case, it could be an environmental problem, but that would be exceptions to the rules. We're not discussing the exception to the rule. We're discussing what happens most of the time. All right, and the last part, C, says at least one car will need repair. So, right, so but what do we got to do? So this is, what's the probability? At least one. So that's, what's the probability? So at least one means this one has a repair, or this one has a repair. So what's the one outcome that we're not looking to find?
3 or more. Wait, what?
At least one car has to be repaired.
0.
I want to know the probability of none. Then we're going to say 1 minus that outcome. So what's the probability that you have no repairs? That was what we found in the first problem, right? We found it. What's the probability of not having a repair? Okay, that would be 0.72 times 0.72. That was part A. So that was the answer we got here, right? And so, okay, there's no way I can write it in that space. That would be 0.5184 because we already found that part. And so my result for this case would end up being what value? 0.4816. Because that would be no repairs times no repairs. That's what we did to start with. And then we say, well, I want everything else. What if at least one of my cars has to be repaired at least one time? Or 2 times? Or 3 or more times? And then you got the other car needing that same repair. And the outcomes would be way too complicated to figure it out the other way. So we figure out the one thing we don't want. What's the probability that neither car needs to be repaired at all? And so in that case, you can look at it and go through it from there. All right, here's 25. Oops. 25 is a two-way table. And it says, a Gallup poll in March of 2007 asked 1,005 U.S. adults whether increasing domestic energy production or protecting the environment should be given a higher priority. Here are the results. And you got that results in the scenario. Increased production, 342, equally important, and all those different values. So the question is, what would we do here? Anybody got a guess? Here we go. Shh. So you can see the picture here. The original question says, the first question says, if we select a person at random from this sample of 1,005 adults, then what is the probability that the person responded increased production? That's exactly right. So it's 342 over 1,005. Okay, that's it. Okay, if you want to write that out, we point 340. Nothing complicated. It's part out of the whole. Part B. What's the probability the person responded equally important or had no opinion?
Wait, on this one, would you do the 30 over the 1,005 and then 50 over 1,005 and then add it together?
Not quite.
Don't you add 30?
You'd add 30 and 50 and 5.
You're going to add 30 and 50 and add them together. Well, you've got which the person responded equally important or had no opinion. So it's 30 out of 1,005 plus 50 out of 1,005. So you're going to get, yeah. Oops, I know. I'll check in a minute. All right, so 30 over 1,005, and it's going to give me 50 over 1,005 to give me 80 over 1,005. That would be the answer to that one. This one or this one. Remember, do we know that this is different? I'm sorry, disjointed? Is it disjointed? Look at your table. It is disjointed. Why? You can't choose two different things. You either chose one or the other. It's kind of like voting. You check one box. If you check 2 boxes, then they would report that as a possible error. And so you've got to make sure that you're keeping up with, is it disjoint or independent? In this case, independence is not a problem. Why? It's or.
Oh, yeah.
I'm not multiplying here. I'm adding. So this one or this one. If it said this one and this one, then that would have been, well, that's impossible because disjointed events are always what? Dependent. Disjointed events, that was one of the multiple choice questions on that one outcome, right? And so, let's move on to another question. All right, let's see. The next question will be 35. I'm going to give you a chance to finish this one. So take a few minutes and work through 35 if you haven't already done that. So 35, you roll a fair die 3 times. What's the probability of that? Now let's pause for a minute. You're having several things happen. You roll a die and you get all 6s. Is this independent?
Yes.
Is it disjoint?
No.
No. Well, I'm not so concerned about that because of what it's asking. The question's really asking, what's the probability of rolling a 6 and a 6 and a 6 and a 6 all together? So, well, because it's independent, we can multiply. 1 over 6 times 1 over 6 times 1 over 6.
So wouldn't we zig out up there?
No.
Okay.
And it would work out. And what would you get? Will be 1/6 cubed. It'd be 0.00. Yeah, so round it to 0.005. So 5 every 1,000 rolls of 3 rolls of die, you would get 6, or you would get 3 6s. Let's look at the next one. You roll all odd numbers. Okay, so part B, what's the probability that you get an odd? How many odd numbers do you have?
1, 3, 5.
So the probability of getting odd would be, what's the probability for that happening? Yeah, it's 1/2. I know you can see it. It's okay. So 1/2, and I want to do this how many times? So it would be 1/2 cubed. So 1/2 times 1/2 times 1/2, 0.125. Because it's 3, this tells me that it's 3 times, how many times I want this to happen. That's why we do it 1/2 cubed. All right, so let's keep going. What's the part, let's see. Let's scroll, let's go on down to look at E.
Wait, is C 4 over 6 cubed?
C is, I'll already read out the solution. C is 4 over 6. What's not divisible by 3? 1, 2, 4, 5. So that's 4 numbers out of the 6. 4 out of 6. Okay? Okay? Probability that none are divisible by 3.
Wait.
So, right? So that would be 4 out of 6 cubed. Or 4 out of 6 times 4 out of 6 times 4 out of 6. We're doing it 3 times, right? So part D would be at least 1 5. So what's the probability that I roll a 5? At least 1 5 means I get a 5. And everything else I could get whatever. So it'd be, what is the probability you get no 5s at all, right? At least 1. That's your key. How would I find probability of getting no 5s? 5 out of 6 cubed. That would be getting no 5s at all.
Then 1 minus.
Then 1 minus. That would give me the result, which would be 0.421. Okay, let's look at E, part E. What's the probability that I get not all 5s?
Didn't you just take what you know from A, from the,
Yes, you could.
because it's the same.
So what's the probability that I get all 5s?
All 5.
Right? So what's the probability that we get, hold on, not all 5s? Well, that would be the same thing as saying 1 minus the probability of getting all 5s.
So it's 0.57.
So that would be, yeah, pretty much. It would be 1 minus what we get out at the beginning, 0.005, to give me 0.995. 1 minus 1/6 times 1/6 times 1/6. What's the probability they get all 5s? 1/6 times 1/6 times 1/6. That's the very first thing we did. And then, so it doesn't matter what number I'm asking. I could be 2 or 5 or 1, because a die is disjoint and because it's independent. It doesn't matter what number, because they're all the same probability. Okay.
That was a good one.
Okay. Let's look at, let's see, what is... So 15. I really want to talk about, let's see, the first one I had you do is... I want to do 3 first, and because it has one phrase that you may not be familiar with. So let's look at number 3. Or this is from chapter 15 now. Right? So 3 says, a check of dorm rooms on a college campus revealed that 38% had refrigerators, 52% had TVs, and 21% had a TV and a refrigerator. So what's the probability that a randomly selected room has the following? So I'm going to give you, absolutely, draw a Venn diagram. That would be probably the best thing you could do. The question is, the one I want you to answer is part B. That's the one that we really haven't said out loud, but it's not complicated. Just want you to know how to think about it. So here we go. Fridge, TV. What we start off with is a Venn diagram because they told us something about both. Because this has jointed outcomes, I have to be careful not to use a tree diagram here. So Venn diagrams work great. 21% had both. So I look backwards. Refrigerators or fridges have actually 38%. So when you draw your Venn diagram, the fridge circle must have a total of 38%. But we've already got 21% in it, right? So what goes in the outside part? So put 17 goes out there. What about in the outside part of the TV?
31.
It's, so 0.31, because you had 52% altogether. We subtracted the 21% period. So now, what's outside of these circles? Just to finish it. Yeah, so if you add all this together, subtract from 1, you're going to get 0.31. So 0.17 plus 0.21 plus 0.31. You add that together, you subtract that number from 1, you get the outside part, which looks like that. The question was, what is the probability that you have a refrigerator or a television, but not both? What is it? How would I do it?
You just add up 0.31 to 0.17.
Perfect. 0.17 plus 0.31. That gives me my 0.48. Because it says, I want you to have either one, but in this case I'm going to qualify it a little bit more than just one or the other. It's one or the other, but you can't have both of them. Normally when I say A or B, you could have both. But when I add that qualification, but not both, you got to remove the both part. And most of you caught on real quick to that. Good. What about neither a TV nor a refrigerator? 0.3. That's outside both circles. Okay, great. Okay, nice. Okay, here's 15. You're dealt a hand of cards, 3 cards, one at a time. It says find the probability that each of the following. The first heart you get is the third card dealt. So this is number 15. So let's just think about it. Getting a card is dependent because I'm giving you 3 cards. So we want to get my first heart on the 3rd try. So I'm looking at getting 2 kinds of cards, non-hearts and hearts. So let's think about it. The first card I get is not a heart. What's the probability that you don't get a heart? Right, which is 40.
Yes.
So you get 40 out of 52 chances of getting not a heart. Oh, you're right. Yep. So 39 out of 52. The next one I get is also not a heart. So 38 out of 51. But the next card I get is a heart. There are 13 hearts left, and there are only 50 cards to choose from. No, it's all at the same time. So it's this and this and this. So it is multiplication. And so multiply all that together, and that'll give you the result.
That's like
1.
0.145.
So you have about 14 and a half percent chance of getting a heart for the first time on the third try. 14.5. 38 over 52 times, or 39 over 52 times 38 over 51 times 13 over 50. Be careful. When I give you events like that to happen, think about it. What would happen the first time and identify that probability? What would happen the second time? Identify that probability and kind of keep that idea going, and you can figure out all the different events. For example, 15 part B would be very similar. That you get no spades.
That's C.
Oh, sorry. Your cards are all red. So it would be 26 out of 52 times 25 out of 51 times, yeah, you just kind of go down the line. You get no spades, then you would do the same, and then we're not going to go on into that, but you get the same, it's basically the same logic the whole time. Here's number 21. This one's about independence, mutually exclusive, stuff like that. In the real estate ads described in exercise 1, 64% of homes for sale have garages, 21% have swimming pools, and 17% have both features. If a home for sale has a garage, what's the probability that it has a pool too? So what kind of probability are we looking at here? What's the probability that it has a pool given that it has a garage? This is conditional probability. So if we write this out just naturally, it's probability of a pool and a garage divided by the probability that you have just a garage. And they pretty much gave us that information. So that would be 0.17 divided by 0.64, which would give me 0.266. Okay, I could also draw a Venn diagram here to kind of help yourself out. Not necessary. They wrote down exactly what you needed, but if it left something out, and you might have to put that Venn diagram down to draw the picture to find the missing part and go through it.
Wait, what was the answer to A?
Answer to A is 0.266. 0.17 divided by 0.64. Any questions?
Oh, probability of both. Point.
Probability of both divided by probability of just the one.